This is an introductory video on discrete probability distributions. I've divided this video into sections so you can scroll to the section you're interested in, but as a guide we'll be discussing what random and discrete random variables are, probability functions, and then looking at a few examples. Alright, let's get started. So let's start with discussing the definition of a random variable. So a random variable is a variable whose value is determined by the outcome of a random experiment, and it's usually denoted by a capital letter. Going back to the traditional variables that we've used in the past, I could say have the equation x plus y is equal to 4. I could have 2x minus 3y is equal to 17 or whatever. So with these traditional variables here, I can essentially solve for x and y. I can move around. If I'm given a condition, I can solve for them. Similarly with random variables, I will get a value for the random variable, but it's not essentially solving for the random variable. And I think that's what we just need to differentiate here with, this term variable from our traditional variables. So again, as I said, with the random variable, we can quantify it, so it can have a value, but it's not really solving it. So what I mean by that, let's have a look at an example. If I say had x, which do you see here, I've used the capital letter X because it's usually what we use to denote a random variable, and X is usually the letter that we go for. You'll see X's, Y's and Z, but X is the most common one that we use. And if I say were to flip a coin, I could say get a head or a tail, and so to quantify this random variable, I'm going to put a value against each outcome. So if, say, I were to flip the coin and get a head showing as the uppermost face, I'm going to say, hey, I'm going to give that value 1. And for tail, I'll give it 0. Now, I'm not limited to just these two. Okay, I don't have to use 1 and I don't have to use 0. They're usually the easiest ones to go about, it's just easier to visualize and to see. But I could have said, hey, if I flipped a head, I got 120. And if I flip a tail, then it's 40. You can use whatever you want. But most of the time you'll be seeing 1s and 0s just because it's easier to visualize. Alright, so just to confirm, essentially what I'm doing here is I'm just trying to quantify a random process. Okay, and a random process or a random experiment means that there must have been more than one possible outcome. So looking at another example, I'm going to say, hey, if I rolled a die and an even was shown, then I'm going to give that the value of 1, and for odd, then 0. Again, you can use any number, but 1 and 0 are usually the simplest. So what I've done, again, I'll reiterate, is I've just given a value for a random process. Now, there are two types of random variables. So a random variable could be either distinct or continuous. Let's delve into that a little bit further and really identify the difference, and then I'll put some examples against them. So a discrete random variable is simply what it means. Okay, it means that the values are distinct and can only take on certain values. Like, for example, the number of students in a class. I can identify that number. The result of rolling a die. Number of cars being sold in a week. Against each of these types of examples, I can put a value to it. No matter how massive the number is, how small, I can still put a distinct value against it. Whereas a continuous random variable can take any value in an interval, and these intervals could be finite or could be infinite. So for example, the height of students in class or the weight of people at work. So say in these two examples, I can't actually give an exact or distinct value. Let me tell you why. For example, my height could be, say, 1.62 meters. But is that really what it is exactly? What if I was actually 1.6213? Or what if I'm 1.62235445 meters? Okay, I don't actually know for certain what that actual height is. Okay, and same thing with my weight. Could be 86 kilos or it could be 86.2134 kilos. I'm not entirely sure what it is exactly. And in cases like this, they're considered continuous random variables. Let's take a look at a few examples and identify whether the following probability distributions are discrete or continuous. So starting with question A, I want to identify that the number showing on a die is either discrete or continuous. Now I can list the outcomes here. I can have either 1, 2, 3, 4, 5 or 6 showing on the die. Because they are distinct, therefore it is discrete. And as you can tell, I could list my outcomes here. All right, for question B, the weight of a randomly chosen student in the school. Well, let's just say the range of weights at a school is anywhere between 30 to 300 kilograms, whatever. Let's say in between that range, somebody weighs 56 kilos. But do they really weigh 56 kilos? Do they weigh 56 kilos exactly? What if they weighed 56.11498 kilos? I'm not entirely sure. Even though I am bound between 30 and 300 kilograms, I've been given a restriction, there is a range here, but because I cannot list every single possible outcome, it is continuous. Because I can't give an exact or distinct value to my outcome, therefore it is continuous. So it's really important to note there. Previously, I was able to list the outcomes after rolling a die, whereas in this case, I can't list every possible outcome, even if my range was smaller and smaller. Okay, even if I was between 30 and 35 kilos, it's not the fact that it is infinite which makes it continuous, it's the fact that it cannot be listed that makes it continuous. All right, now we want to state whether the probability distribution of what year a student was born in at a school is discrete or continuous. Now I could say have at a school somebody being born in 1987, 2013, 2005, 1998, whatever. Now the concept of time is infinite. And you might think, well, I can have an infinite possibility of years, that I can list here. It's all relative to the question. And okay, you're right. Even if something is infinite, it doesn't make it by default continuous. As long as it can be given a distinct value, it is discrete. So in this case, because I'm asking what year is it, well, there is no doubt about it. If they were born in 1987, they are born in 1987. They're not born in 1987.7654. Okay, they're born in 1987. So in this case, it is discrete. Question D, the length of somebody's foot. Well, again, let's have a look and say, let's say the length of somebody's foot is anywhere between 10 and 40 centimeters. This question is very similar to the question we looked at previously in regards to weight. So I can't really be sure how long something is in particular, and I can't list it because if somebody is, say, has a foot that's 15 centimeters long, am I really sure it's 15 centimeters long? It cannot be listed, and so therefore it is continuous. And finally, the ATAR result for a particular year. Now, I do not have an infinite possibility of outcomes here because I know ATAR results are restricted to 2 decimal places. That means I will have distinct values. So if somebody got 98.05, I know for sure they actually did get 98.05. This isn't ambiguous. Like, it's not like, oh, did they get 98.0543? Okay, no, they actually got 98.05. That's the measure of ATAR, and so in this case, it is discrete. Before we go ahead and look at examples, let's just discuss the notations that we're going to see and use. The capital X represents the random variable. We've already discussed that. The lowercase x represents that particular value, so say the number of heads. P of x represents the probability of x, and in this case, just in this example, we're talking about the random variable. When I've got it looking like this, P of capital X is equal to lowercase x, this refers to the probability that the random variable x is equal to that particular value. So we call this the probability function, and we're going to look at how it comes into use in more examples. So just to add to this, to work out the probability that a discrete random variable x takes a particular value of lowercase x, we need to identify the event. Okay, so we need to set out all the possible outcomes that correspond to it. So the function used to describe the probability distribution of a discrete random variable is the probability function, and it exists in the real plane, and it can only be between 0 and 1. In this example, I want to know what the probability of getting 3 heads is when I throw 4 coins into a bucket. So I've just put together a tree diagram, very straightforward, and we know each one of these arms, obviously, for a fair coin, each arm is going to be half and half. There is a 50% chance of getting a head and a 50% chance of getting a tail. And as you can see, if I say we're to get head, 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 the probability here is going to be half times half times half times half, and that gives me 1 out of 16. And you can agree that each one of these outcomes is going to be exactly the same. They're all going to be 1 out of 16. Okay, but in this particular example, I'm concerned with getting 3 heads. Okay, so if this one has a 1 out of 16 chance, and this one is 1 out of 16, and this is 1 out of 16. So from this, I can now establish the probability of getting 3 heads. Okay, and I'm sure you can tell it's 4 out of 16, but I'm just going to discuss how we're going to come about writing this. So if I wrote it like this, P of capital X is equal to 3, you can see that the capital X there is my variable, and I'm after the value 3. Now, what does this 3 represent? This 3 is representing number of heads. Okay, and so from that, I know the answer is 4 out of 16, as we've already established. But I just want you to be familiar with how we interpret this. Okay, because we've set this ourselves up as representing the number of heads. Well, the question did not ask us to put it in a table, but if we were to put it in a table, you can see that this is how I would write it up. This is the probability function and what it looks like. So this is now, I want to know the probability of getting the random variable of no heads. Okay, and there's 1 out of 16. Of getting 1 head, 4 out of 16. 2 heads, 3 heads, and so on and so forth. Okay, in this example, a fair 6-sided die was rolled. The event space for this random procedure is obviously 1, 2, 3, 4, 5, and 6, and the possible outcomes are equiprobable. This means that the chance of rolling a 1, 2, 3, 4, 5, and 6 are equal, and we know that it's 1 out of 6. So let's have a look at this a little differently. What if now I want my random variable to actually be the number that appears uppermost on the face after the toss? That means it can be either 1, 2, 3, 4, 5, and 6, and obviously no other values. Sorry, excuse that typo there, and no other values. And it's obviously discrete values, and in this case, integers. So I would write this as this, my probability function is equal to 1 out of 6 if I get a 1, 2, 3, 4, 5, and 6, or 0 if it's any other number. So a die is thrown. Write the probability distribution of the number shown on the die and graph the distribution. So each value has a probability of 1 out of 6. So the table of distribution is super simple. Okay, we've got X, and then I've got X, then I've got my probability function. My outcomes are 1, 2, 3, 4, 5, 6 over here. That's what my values are in this example. And if you were to sketch that on a graph, it would look like so. Very straightforward. So I've got the values here along my x-plane, the probability of these variables along the y-axis, and then I've marked them on the graph as such. Simple as that. So in this example, I've got Sarah competed in the 800-meter race 20 times last year, and she placed in the top 5 for all 20 races. The following table records her results. Okay, and she's come first 3 times, second, we don't know how many times, third, 4 times, fourth, 5 times, and fifth, 3 times. So for question 1, I want to determine the probability that she finished second last year. And for question 2, what was the probability that she earned the medal last year? Okay, let's start with question 1. I want to find the probability that she finished second last year. Well, I wasn't actually told how many times she came second. Okay, coming back here, I was told though that she did compete in 20 races. Okay, so what I've done here now is I've added 3 plus 4 plus 5 plus 3, and that gives me 15. And so obviously that means she came second 5 times. And then finally, the probability is really simple. But how I would write this out is I would say probability of the random variable of 2, so this is the value that I am after, that she came second, is equal to 5 out of 20, and you could either leave it in fraction form or in decimal form. For question 2, I want to find out the probability that she earned a medal last year. Well, we know that she can only earn a medal if she comes first, second, or third. Now, I've just continued this table here where I wrote the probability of each outcome, and that was just simply like over here. The chance of her coming first was obviously 3 out of 20. Coming second was 5 out of 20. Here's 4 out of 20. It's relatively straightforward. 5 out of 20. And that's how I got those values there. 3 out of 20. Okay, and this is how I got these values here. So, what's the probability that she earned a medal last year? Well, As I mentioned, she needs to come either first, second, or third, and she managed to obtain a medal 12 times. I've written it like this, and it's the same as 3 out of 20 plus 5 out of 20 plus 4 out of 20, and that leaves me with 0.6. Again, you could have left it in either fraction or decimal form. And for the final example, I want to find the unknown constant A in these probability distributions. So I've got the values 1, 2, 3, 4, and 5, and the corresponding probabilities written below. But how do I find out what A is? Think about it. Remember, the probability of every single outcome should equal to what? It must equal to 1. So if I add these all up, okay, each one of these probabilities, if I add them up, it must equal to 1. So it now looks like so. I've expanded that first bracket, leaving me with that. I've then collected the like terms, and I'm left with 4a squared minus 5a plus 1 is equal to 0. As you can see, it's just algebra from this point onwards. I'm then going to factorize this quadratic, and I'm left with 4a minus 1. A minus 1 equals to 0, and that is a equals to a quarter and a equals to 1. Now, if you left your answer like this, you will not get full marks. And why is that? It's because I actually do need to test each one of these and see if it actually satisfies. Okay, remember, your probability must lie between 0 and 1. I can't have any negatives. Ignore that dot. I can't have any negatives, and it can't be greater than 1. So let's try and plug in a quarter into each one of these. So a quarter in this first one is equal to 5 out of 16. This satisfies. Over here, it's equal to 3 out of 16. It satisfies. This one is equal to a quarter. It satisfies. This one is equal to 0, and this is equal to a quarter. Beautiful. So a equals to a quarter works. Okay. Now let's try a equals to 1. If I sub that in, I get 2. Oh, already this is incorrect. Okay. I cannot have a probability of 2. So I'm not even going to bother to try the rest. And look, you can already see this one is 3, but I'm not going to bother to try the rest. It does not work, so therefore it's only a equals 1 quarter. If you enjoyed this video and found it helpful, please don't forget to hit the subscribe button before you go. And also check out our social media pages across all the platforms under Ask Cassie.